Hello friends, I welcome you in lecture number 20 on complex differentiation. In this lecture we are going to discuss about analyticity of elementary functions. We are familiar with elementary functions of real analysis, and now we are going to discuss about elementary functions of complex analysis, and those elementary functions are exponential function, logarithmic function and trigonometric functions. We will discuss all these elementary functions one by one, and we will discuss their analyticity also together with their properties. So in this lecture we will discuss about exponential function, and then we will continue with this discussion of elementary analytic functions. Now if we have some complex variable denoted by z equal to x plus iy, then exponential function of this complex variable is denoted by e raised to z, or they use this notation also, expz, that is exponential of z, and is defined in this way: e raised to z, that is e raised to x plus iy, and this we can write as e raised to x times e raised to iy, and using Euler's formula, e raised to iy is nothing but cos y plus I sin y. So we consider this as definition of complex exponential function, and that I have written here systematically. They can ask you to write down the definition of complex exponential function or simply exponential function. Let z is x plus iy. The complex exponential function of this variable z is denoted by e raised to z or expz, and is defined as e raised to z equal to e raised to x times cos y plus I sin y, and here y is angle and it is measured in radians. We use radian measure for this angle y. So definition is simple. You can simply put z equal to x plus iy, then you have e raised to x plus iy, that we can write as e raised to x times e raised to iy, and using Euler's formula we put e raised to iy equal to cos y plus I sin y. Now we prove that this complex exponential function is analytic everywhere in the complex plane, or we can say that e raised to z is entire function. So that is easy to prove. Now we are familiar with the method of proving the analyticity of a given complex function. So here our function is e raised to z. So first we write f of z equal to e raised to z, and e raised to z is by definition e raised to x times cos y plus I sin y, and this we can rewrite as f of z equal to e raised to x times cos y plus I times e raised to x into sin y, and this we can compare with u plus iv, say, to write down real and imaginary parts of this exponential function. So if we compare this with this, we have u equal to e raised to x times cos y and v equal to e raised to x times sin y, and we know how to prove given function is analytic in some domain. First we have to check the satisfaction of Cauchy-Riemann equations, and that will give us the idea of differentiability, and then using the definition of analytic function we will be able to determine the points at which this function is analytic. And here we have already written that e raised to z is entire function, that is we are proving that e raised to z is analytic at every point in the complex plane. So we must have satisfaction of Cauchy-Riemann equations at every point. Now first we find out partial derivatives of u and v. Del u by del x is cos y is constant, derivative of e raised to x is e raised to x, and del u by del y is e raised to x constant, derivative of cos y is minus sin y. and here we write partial derivative of v with respect to x, sin y is constant, derivative of e raised to x with respect to x is e raised to x, del v by del y is e raised to x as it is, derivative of sin y is cos y. And now we can see that del u by del x is e raised to x cos y, del v by del y is e raised to x cos y at every point. Therefore, this equation is satisfied at every point. Similarly, if we consider negative of vx, we have minus e raised to x sin y, and here also we have minus e raised to x sin y. So we can say that this minus vx and del u by del y are also equal at every point. So we can write that these two are equal at every point, denoted by z equal to order pair xy in the complex plane, or we can simply write in the plane. Whenever we write that something is true in the plane, that means we are in the complex plane. So this is now satisfaction of Cauchy-Riemann equations at every point in the complex plane, and we can see that all these functions are clearly continuous functions of two variables. They are elementary functions, exponential and trigonometric functions, sine and cosine. So we can write continuity condition also clearly, del u by del x, del u by del y, del v by del x and del v by del y are continuous at every point. They are continuous at every point z equal to ordered pair xy in the plane. Therefore, both the conditions of differentiability are satisfied at every point in the complex plane. So what we obtain, we find that f of z equal to e raised to z is differentiable at every point in the complex plane, or we can simply write differentiable everywhere. Differentiable everywhere, that means it is differentiable at every point in the complex plane, and the function which is differentiable everywhere is analytic everywhere. Therefore, f of z equal to e raised to z is analytic everywhere or analytic at every point in the complex plane, and the function which is analytic everywhere is known as entire function. Therefore, we have shown that e raised to z is entire function. So this is important property of exponential function. We can consider this as one property of complex exponential function. It is entire function or it is analytic everywhere. And if we wish, we can write the formula for derivative of e raised to z also. From this discussion, we have shown that it is differentiable at every point in the complex plane, and we know that f dash z is given by del u by del x plus I into del v by del x. F dash z means d by dz of f of z, and del u by del x is e raised to x cos y, and del v by del x is e raised to x sin y. So here we have e raised to x into cos y plus I times e raised to x into sin y, and we can observe that e raised to x is common here, and here we have d by dz of f of z, which is e raised to z. We take e raised to x common, and here we are left with cos y plus I sin y, and this is nothing but e raised to z by the definition. So here also we find that derivative of exponential function is function itself, and this is true for all z in the complex plane. So this property is similar to the property of real exponential function. We know that if we have real exponential function e raised to x, then it is differentiable everywhere and its derivative is function itself. So same property is true for complex exponential function also. So they can ask you to prove that e raised to z is entire function, or they can ask you to prove this formula that d by dz of e raised to z is e raised to z at every point. So all we have used is this formula to write down the derivative, and to prove the differentiability we have used Cauchy-Riemann equations. So we will continue with this discussion of elementary analytic functions in upcoming lectures. Thanks for watching.